Hello again, I'm Peterman the Internet Electrician, and welcome to another one of my video shorts on current topics at electrical-online.com and right here on YouTube. In today's video, in my series of electrical testing devices, we're going to work with a digital multimeter. Now, of all the devices available for testing electrical systems and circuits, this is by far the most versatile and useful, the digital multimeter. For this particular video, I'm going to use my own personal meter, and it's the Fluke 189 True RMS multimeter. Now, this meter is more sophisticated and expensive than most DIYers would need for the jobs we're going to do around the home and the ones we're going to focus on in today's video. You can get a perfectly good meter for anywhere from, say, $30 to $100 at your home improvement store. This meter is no longer listed on the Fluke website, but they were upwards of $600 when they were new, and you can still buy them today on Amazon. I found a used one for around $100, right to one that was still in the box for sale for around $600. Just remember that when you are purchasing a meter, make sure to look that it's UL or another accredited agency approved for the use, and that you're buying it from a reputable place like a home improvement store is good, or if you're doing it online, check for those approval ratings as well. And another thing to check for when you're buying a multimeter, you really don't need a true RMS multimeter. RMS or an averaging meter will do just fine for most purposes around the home. So there's lots of tutorials out there on YouTube that go through a multimeter extensively and go through all the functions that they're capable of. But for the purpose of my audience, I'm just going to stick with things that you would do around the home for the average do-it-yourselfer. We're going to deal with just measuring or testing voltage, both AC and DC. We're going to measure and test for continuity or resistance. And then we're going to measure and test some current flow, both AC and DC. One of the things to consider with a less expensive meter is that they're not likely to be auto-ranging, and you usually will have to select a voltage range that you're expecting to test for to get the best accuracy. So for example, if you're looking at testing a 12-volt battery, the cheaper meter might just say DC volts and then several ranges to select, like 20 volts, 200. So if you're, say, checking a 9-volt battery, you're going to go to volts DC, and then you're going to select the range of 20 volts if that's the nearest to 12 and exceeding it. You're going to select 20, and then you're going to test your battery, and that'll give you the most accuracy. Anyhow, let's go through some of the basic functions and start with some testing using my Fluke 189. So let's just have a closer look at the meter here and some of the basic functions of the dial here. Going clockwise, we have volts AC, then we have millivolts AC, volts DC, you've got millivolts DC, and resistance. Those are the main functions we're going to be using, is volts AC, volts DC, and ohms for resistance. And then also we'll touch on amps, milliamps and amps AC, and milliamps and amps DC. Now you see we've got a warning on the screen, leads. So as soon as you go to the amps function, they want to make sure that you put the test leads in the proper locations. We'll get into that when we start testing for voltage or for current. But let's start with voltage. Let's test a battery. So the essential part of a digital multimeter is a good set of test leads. Now they will come with test leads, and you usually have a red and a black. And they come with alligator clips too, that these particular ones they thread on. So when you need to free up your hands, you can clip onto what you're testing with these alligator clips. And now important to know where these meter leads go when you're testing for voltage or current. So always your black lead goes into the common terminal. Now for voltage testing, I'll give you a close-up look at this. But this, anything for volts up to 1,000, your red lead goes into here. The other terminals, this is up to 400 milliamp fused terminal here, and this is a 10 amp fused terminal for current testing. We'll get into those later, but right now we're on voltage. So into the common, into the terminal marked volts. So first off, let's test a standard D-cell battery. You should expect about 1.5 volts out of a fully charged or a fully new battery. So again, we're looking for voltage DC. So on our dial, we select volts DC, not millivolts DC, but volts DC. Now, put your black lead on the negative side of the battery. Can't even use the alligator clips on these because you nothing to grab onto. So there you see my black lead on the negative side of the battery, my positive lead on the positive terminal, and there we have 1.6138 volts. Now don't worry if you do reverse the leads. If you put the negative on the positive of the battery and the positive on the negative, your meter is going to tell you that you've got the terminals switched because you're going to have negative 1.6 volts. Let's test another battery and I'll show you where the alligator clips come in handy. These particular ones thread on to the lead. Make sure that's nice and tight so you get a good accurate reading. Now on this 9 volt battery, the positive is this terminal here. Let's connect our alligator clip to the positive terminal. We'll reset that. And then take our negative lead without the alligator clip and check that. And there you can see we have 9.533 volts. Now, as a bit of a side note here, when you're testing batteries, to see that there's voltage there, open circuit voltage does not necessarily mean that the battery is good, because you need to put a load on it. So let's just demonstrate that. I've got my leads hooked up to this 9 volt battery. You can see I've got 9.4 reading on the meter. And I've also got this little tester. It's a 12 volt tester, but it'll light up with 9 volts if the battery's good. So what you want to do is make sure that even under a load, that battery is going to provide that load. And you can see it lights up the tester. The voltage drops to about 8.5 volts, and then it bounces right back to over 9. So that's a good battery, decent battery at least, you know, because it will still show a voltage under load. Let me show you what happens with a battery that's done its time. So let's check this 6 volt lantern battery then. Now without a load, we'll connect my alligator clips to the negative, black to negative again, red to positive. Oh, there we have 5.8 volts, so not bad on a 6 volt battery. You might think that this battery still has some usefulness left in it, but let's try it with a load. Okay, again, here we are with a load on it now in our little 12 volt tester, but still should light up with a good 6 volt battery. You just get about half the brightness out of the bulb. But let's have a look what happens when we put a load on this 6 volt lantern battery. You can see we still have 5.8. Put a load on it, and that battery voltage just crashes right down to near zero. Not even a flicker out of the tester. So you know that this battery is no good. They do have other devices for testing batteries that put a load on them as well and can give you a load and time test. But this is one way to tell if a battery is any good. Put a load on it because they show good when they're open circuit, but they just can't provide any load. Okay, so let's test for some AC voltage. Now here's a standard kitchen outlet. In my kitchen here, it's a GFI outlet, and we'd expect about 120 volts. So again, your meter leads, black in the common, red in the voltage port. Now we select on our scale voltage AC. The little sine wave squiggly line is AC voltage. And you can see we've got about 0.1 on open circuit here. I'll just touch those leads together to make sure we got as close to 0 volts as you can get. So now we'll try hot to neutral, and we should expect about 120 volts. Now this is a tamper resistant outlet, and the functionality of those says that you have to be plugging in a plug with 2 prongs or 3, but you have to have the 2 prongs plugged in and push them in at the same time or they're not going to go in. Look, I'll try to get the neutral in. Won't go by itself, nor will the hot. But the functionality of tamper resistant is that if you hit them at the same time, apply their equal amount of pressure, they'll go in. So there you have it. get my hand out of the way. And we've got 119.9 volts in this outlet from hot to neutral. So now we'll check hot to ground. So we'll leave the probe in the hot terminal. And we will touch the black into the ground. Make sure we got a good connection in there. And now you can see with the red lead in the hot prong of the receptacle and the black on the ground, we've got 119.6 or 7 volts, the same as we had hot to neutral, what you'd expect. And now you can also check the plate screws and see if you've got a ground on those plate screws. Leave the hot terminal in, hot probe in, and you kind of got to dig in on that plate screw because it's painted, so you got to make sure you get a good contact there. And again, you got 119 volts from hot to ground. So I've shown you testing for power in a receptacle, and now of course you can't do that with a switch without opening it up. Now the reason you would be using your meter to test for voltage around the home would be if you're going to work on something, replacing a switch or a receptacle. So obviously the best method is to open up that box and get right at the wires, because you might have noticed or you might have experienced it when you're putting the probes into a receptacle like we did. You can't always be sure you're getting a good contact in there because the probes aren't designed to go into that hole. An actual 120 volt plug is with nice flat blades is supposed to go in there. So you can't be sure you're getting a good contact, and thus you can't trust that there's no power there when you go test with your meter. So if you're doing it, you want to shut off the appropriate circuit and be relatively certain that it's off. But the final test is to use a meter like this to check before you start working on it. So with a switch opened up like this, again, meter leads, black and common, red in the voltage probe, turn it to volts AC. Now I'm going to put an alligator clip on, and I'm going to get a good solid bite on that bare ground wire with my alligator clip. Then using my red probe, I'm going to check right at the bare wire, which is hooked to the terminal, to see if we have voltage. So let's have a look. This is a switch that just is a switch leg drop, which incidentally is no longer allowed to just use the white wire as a hot like this, but this house was wired before the code changed. So that wire should be marked as black, and I see the electricians that did this didn't do that. So we're going to do that before we're done. We're going to take a black felt pen and color that white wire in because it's used as a hot here, but that's off topic. Let's just check. And we have 120 volts on that terminal. So we need to shut that breaker off and again check to make sure we got 0 if we were going to be working on this circuit. For example, changing this switch. So there you've got power on the white and you've got power on that black terminal. Now I've got the switch upside down, so down is on and off is up. So I'm going to turn that off. And then we should only have power on one terminal, and that's the white, which is being used as a hot in this case. So there you see 120 there now on the white, and nothing, close to nothing on the black. We have less than a volt there. That would just be induced voltage. Double check to ground. So both leads are touching ground, and you have 0 volts, 0.000. Okay, so now we're going to test for DC current flow. So we're going to use my little test light again. That's a 12 volt test light, but we're going to use a 9 volt battery. So we'll get about 75% of the power that you'd expect to see on that output, I should say, on that little test light. It lights up nicely on a 9 volt battery. We'll set up a circuit. Now, to get current flow, you need to get into the circuit and in a series loop, because what you're doing is measuring the current that's going out of the battery through the test light and back through the meter to tell you how much current you're actually drawing in that circuit. So let's set up this simple circuit. We've got the negative on the negative of the 9 volt battery, then over to the test light, and the probe here is open now. So what we need to do is complete the circuit by putting one lead on that probe. We'll use the black just to get the correct reading on the meter as far as positive current flow or direct current flow, conventional they call it. So we're going to hook that lead to there, and this lead to the positive, and we should see current flow, but we have to set up our meter first. So remember, you've got black on the common and the red on the voltage probe. Now, if you want to check for milliamps or amps, you got to go to DC amps, way over here. So if you forget to move your leads and you switch this over to amps DC, tells you right away your leads are wrong. So you need to go put that in. Your red lead, common stays the same. Your red, we're going to go to 10 amp max. And now that warning telling you your leads are wrong goes away. Likewise, if you have your leads in the amp terminals and you go back to volts, the meter alarms again telling you your leads are wrong if you were going to check for volts DC. So if you check now for voltage, you're going to have a short circuit, because really what you're doing is setting up a series loop, direct line through your meter to measure the current. So if you check for voltage, you'd have a dead short and blow the fuse that's in your meter. So amps, DC, one lead on the negative of the 9-volt battery, through the light bulb in the test probe. Now we're going to connect the black to that. And now the red to the battery. All right, you can see our test probe is lit up. We have a circuit, and that DC circuit is drawing 0.23 amps of DC current. And for AC current, if you were going to set up a similar circuit using an AC source, again, you have to get those meter leads as part of the circuit. So in a series loop with the circuit, and then it'll measure the AC current. So now let's talk about the resistance or ohms function of your meter. So what are ohms? Well, that is a measure of resistance. So when would you use that? Let's say you've pulled some cables in your basement rough-in and you got mixed up on which wire is which. So you need to know that this wire at the panel is the same wire over at your outlet box. So there's a couple ways you could do that, but without power or voltage on the circuit, the best way would be to take the positive or the black wire at one end and just connect it temporarily to your ground wire, and then go back to the other end where you're trying to find out if it's the same cable, and you measure for resistance between black and ground. When you find it, you break apart that circuit again just to verify that that's indeed the cable you're looking for. There's many other reasons you'd want to check resistance, measuring resistors and such, but just remember that the lower the resistance, the more current flow, and the lower the resistance, you know that you're actually measuring a cable that you might be looking for. So here we are, open line, OL, is the highest resistance. That's infinite resistance, because what we're doing here is we're just measuring the thin air, and there's tons of resistance to current flow because there's no connection between these two probes. So if we connect them together, this is how you want to test to make sure your meter's working with it set on ohms. So connect those leads together and you get right down there to 0.12 ohms, so very, very little resistance to current flow. If we put voltage on these wires now, they'd just blow apart because it would be a dead short. Very low resistance, very high current. High resistance, low current. So that's what you would expect to find if you connected that black wire of your cable to the ground, went to the other end of that cable. You would see something close to 0 ohms resistance between the black and the ground. All you'd see is the resistance of the wire itself in the loop, going from where you're measuring to where you shorted them out. So there you go, two leads together, very low resistance, 0.09 ohms, and with no connection, very high resistance. So just to show again, your leads together, very low resistance to current flow. Your leads apart, infinite resistance, tons of resistance because it's just air. Does your body conduct a little bit? Let's try. One lead on each thumb, and there we have about 250 kilo ohms of resistance through my body from one arm to the other. So now let's see what kind of resistance we have across that little light bulb that's inside this test probe, test light. So we'll check that and go to this one. And there we have about 20 ohms of resistance through the filament on that little test light. About 20 ohms there. And that resistance would go up considerably once you put some voltage on it, because then the heat gets involved here with the current flow, and that makes the resistance of the filament go way up in a tungsten lamp like that. But there you have about 23 ohms just across that with no voltage. Incidentally, if you check this test light with a resistance check like this and you found nothing, then you're going to know that your little light bulb is burned out inside your test lamp and it's no longer useful. And as you can see, I colored in that white wire that's being used as a hot in this switch leg drop. Just colored a good length of it with a black felt pen, just to show somebody down the road that that wire is indeed a hot wire and not a neutral. Thank you for watching. I hope that you learned something useful from this video. My goal is to help you out with your small home electrical projects or minor repairs, and to help you complete them both safely and competently. Please feel free to like, comment, share, and subscribe to my YouTube channel here. And for more helpful information, visit my website at electrical-online.com. And if you'd like to learn more about home electrical, my program, The Basics of Household Wiring, is simply the best electrical educational information you will find, and it's available as a DVD or an instant download. I also use this information as the core material for my best-selling course at udemy.com called Learn the Basics of Household Wiring, the Electrical System A to Z. And of course, you can find me on Facebook and Twitter. But what if you need help with something right away? I'm one of the experts on the Magnify app. That's Magnify with an I. You download the app and search for the Internet Electrician from your smartphone. You can get instant assistance. And I'm also a certified expert on the JustAnswer.com team. There are links below in the description here to everything that I've told you about. So until next time, thanks for watching. I'm Terry Peterman, the Internet Electrician.